Hello everyone and welcome back to Unit 1 of the iGCSE Computer Science syllabus with me, CS with Mr. G. Today we're going to look at negative numbers using binary. So how to use this method called 2's complement in order to represent positive and negative 8-bit binary integers. So we should already be familiar with this term 8-bit binary integers, which we've discussed so far. So we should know what 8 bits equals a byte, and we should be familiar with how binary is stored and converted into denary. We are going to convert positive and negative binary numbers using this method called 2's complement and be able to work both ways. So working positive into negative and negative into positive. This is going to be a short lesson, but I do recommend that if you haven't followed the lesson so far with binary, then go back and give those videos a watch just so you're familiar with the binary number system and how it works. So far, we have looked at the representation of positive numbers. So how to store a positive denary number in binary, for example, using our conversion chart. And like I said, if you haven't followed the lesson so far, please go back and give this a watch. Binary is quite simple. Whoops, I missed the floor there. But yeah, there's 8 bits, that's a byte. And this has all been discussed thus far. So for negative numbers, we use a system called 2's complement. And the method is quite simple. If we want to work out a negative number in binary, we first convert the number from denary into binary. So using our typical chart above and following the steps that we followed so far. Then once we've got our binary number, so the ones and zeros, we simply flip them around so that 1 becomes 0 and 0 becomes 1. Once you've done that, all you need to do is add 1 to the number. 1, 2, 3 are the steps. And like I said, this is a fairly simple lesson and it shouldn't take us too long to understand. Okay, so steps 1, 2, and 3, and we'll run through some examples now. The first one we're going to do is calculating negative 15. So we need positive 15 in denary, which is here for us already. As we've learned, 8 add 4 add 2 add 1 equals 15. And to convert this into negative 15, we need to flip all the bits around. So 0 becomes 1 and 1s become 0. So just to confirm, there's our answer. And then the third step was to add 1 to the number. Now adding 1 just means to put a 1 here. So if you want to, you can fill the rest of the gaps in with a 0. But when you add 1, it simply means the number 1 in this first column here. So if we're adding 1 to this number, okay, not the top number, we do 1 add 0, which is 1. This is the same. And this all stays the same. So the only time you might have a problem with this is if you've got a 1 in this first column here, and you'll have to put 0 and then carry the 1 over. Okay, but this case it wasn't. This was a 0. Ignore that carried 1 there. And this is the answer to the question, negative 15. Just to confirm, there you go. We'll do another one. This time we are given the negative number. So this is a negative number in binary and we have to figure out what it is by using 2's complement. So the first thing we do is invert the bits. Like so. Just to confirm, bits are inverted. Then we add 1. So the same again, it was simply 0 add 1. So this was quite simple. And then to convert this into denary, add the 1s, so it's 1, add 2, add 4, add 8, add 64. We're just looking where the 1s are in our columns and adding them up. So 64 add 8 is 72, plus the 4, 76, plus the 2, 78, plus the 1 equals 79. So just to confirm, we added 1 and the number was 79. So the first number was equal to negative 79. Okay, we worked the other way around this time, but the method stays the same. You flip them all around and add 1. Before we go and do some examples of the conversion into 2's complement, first we need to pay a little bit of attention about how it actually works. We tend to work with 8 bits or a byte at GCSE level. As we discussed before, 1, 2, 4, 8, 16, 32, 64, and 128. The biggest number we can store with these 8 bits is 255. If we've got all 1s in these columns, all the numbers at the top added together equals 255. The smallest we can have is 0. If they're all 0, then the number is 0. So typically, we can have 0 to 255 using these 8 bits. Now, what 2's complement does is it sacrifices this first bit here, where it simply becomes a sign bit. Now, a sign bit is just a bit that tells us whether the number is positive or negative. And as we go through some of the examples, you'll start to notice that negative numbers start with a 1 and positive numbers start with a 0. So this is something that you need to pay attention to. Once you've converted a number into negative using 2's complement, Just pay attention to make sure if you're working with a negative number, the first number should be a 1. If it's a positive, the first number should be a 0. Okay, so pay attention to these rules. So because of that, that means we can't store the values over 127. Because as we know, 128 would be 1 here and then all zeros. But in 2's complement, this isn't the case because this column is our sign bit. It doesn't represent positive 128 anymore. So the biggest number we can store means all of these being on. So 1, 1, 1, 1, 1, 1. And then the first number would be a 0. So the biggest number we could actually have is 127. Don't worry too much if you're not following that or you don't understand. As long as you remember that 0 at the beginning means a positive number and 1 means a negative, then you should be okay. The steps to follow are simple. Flipping numbers around and adding 1 is a simple process to follow. Just bear that in mind. Okay? So instead of 0 to 255, our range now shifts from -128 to -1 and 0 to 127. So we've effectively got -128 to positive 127. Okay, that's our range of numbers using 2's complement when we are working with a byte, 8 bits. And to finish off with some practice questions, which by all means give the video a pause, give it a go, and I will explain the answers right away. Before we give these questions a go, I'd just like to point out that in any exam, you will always be told which way round to convert. So for example, they will tell you if it's already in 2's complement, so that we know that the first bit will be the sign bit, so we can then figure out if it's negative or positive. Or they might simply, like this question here, question number 1, convert the decimal number -27 into an 8-bit 2's complement binary representation. So we've been given the number and we have to simply work it out in 2's complement binary. Okay, so the first step, we draw out our chart and figure out what 27 is in normal binary. So we take our 8 bits, we work out 27, which we know is 16 plus 8 is 24, plus 2 plus 1 equals 27. The rest are 0. And then we flip them all around. So 1, 1, 1, 0, 0, 1, 0, 0. And then finally add 1. And if you want, you can just fill in the gaps here to make it easier, because we're simply adding the 1. And we can ignore this first number. We take the 1, we add it onto its 1, 0, 1, 0, 0, 1, 1, 1. And that's our answer. So the answer is 1, 1, 1, 0, 0, 1, 0, 1. And this is equal to -27. Now we have an 8-bit binary number, which is already stored in 2's complement, and we're going to figure out what the decimal value is. So as it's in 2's complement, we look at the first number and we know it's a 1. So we know the number is a negative number. We just have to figure out what number it is. So the same steps apply. We flip it round, so it becomes 0. Let me zoom in to make it easier. 0, 0, 0, 1, 0, 0, 1. Add 1. And it becomes 1 plus 1 is 0. Carry the 1. And then it's 1. And then 0, 1. And then the rest are zeros. And if I take this number here, I know that 1, 2, 4, and 8. It's the 8 plus the 2, which equals 10. So after we follow the steps, we're left with the number 10, which means the original number must have been -10. So what is the decimal value? Well, it's simply -10. Another way you can do it, which some of my students prefer, is if we take the binary number, which is 1, 1, 1, 1, 0, 1, 1, 0. So this is the original binary number here. And then what you can do is in the first column, rather than put a positive 128, is start with negative, and you can work backwards. Now, when we work like this, we're starting off with -128. So that means when we add a number wherever there is a 1, which I'm going to highlight now, we're typically working backwards. So -128 plus 64. So -128 plus 64 equals -64. So we're working back up. Imagine a number chart in primary school. We're working back up our numbers. Plus 32, that leaves us with -32, plus 16, so we're on -16. We don't add 8 because it's not highlighted. Then we add 4, which leaves us on -12, and then 2, because it's highlighted, -10. So that's another way around you can work it. As you can see, it's -10, which was the number that we were given. So you can just simply flip the first number around to -128 and work backwards. And finally, what is the range of values that can be represented using an 8-bit 2's complement system? As we mentioned, the first bit is a signed bit, which simply represents positive or negative, and then we're left with only 7 bits. So the smallest number is 1000000. No, one more zero, which equals -128. If we use the previous example and we start off with our 128 in this column, 128. As you can see, -128, add nothing, is still -128. So -128 is the smallest number that we can store. The biggest number is 0111111. As we said, this number here is the sign bit, so it doesn't represent any numbers at all. And then we're left with 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which equals positive 127. So the range of numbers is -128 to 127. We sacrifice the first bit to represent a different range of numbers. It's not a smaller range of numbers, it's just a different range of numbers because we're still using 255 values, just a different set of values. And that concludes negative numbers in binary. So I hope you've managed to follow along. We've covered all conversions between binary, denary, and hexadecimal. We've covered binary shifts, we've covered binary addition, and finally we've covered binary negative numbers using 2's complement. The remaining lessons in Unit 1 are all to do with how we store data such as text, images, and sound. So there's still mathematics involved, but it'll be specific to the file type that we'll be discussing. So please follow on for the remaining lessons and we can tick off Unit 1. Okay guys, thank you for watching and I'll see you next time.